Wow, what a cool thingamabobber. I think I want to take this home. Oh, so heavy. Oh, I can't pick it up. Walrus, do you think you can help me pick it up? Yes, we can pick it up together. Let's try to lift it. Oh, so heavy. Oh, can't possibly lift it up. But I want to put it in the back of my truck. Well, we have to figure out another way to lift it up. Let's see here. Oh, maybe we can use physics. Yay! Okay, let's see what we can do. Oh, look over there. Oh, this could be pretty cool. Maybe we can, let's see, put this one on top of there. And, oh, this looks pretty interesting. What if we slip this one down below there? And then, let's see if we can lift this thing up. So, pushing here. Oh, so easy. Whoa, that's so easy to pick up. Wow. If we try to lift this thing up over here, it's way too hard. But just using this lever, it's so easy to pick up. I wonder how this could be. It must have something to do with physics. Yay! Well, let's take a look at this here. So very strange. That's too much force. I can't pick this up all by myself. I need more force. But if I come over here and push on this side, then it's easy. Gosh, Walrus, what do you think's happening? Well, one thing I'm noticing is about distance. Watch what happens here. We push on this side and we push a really big distance on this side, and the weight only moves up a small distance on this side. Let's use a ruler to help us out. Let's see, over on this side, we're pushing down a big 7 or 8 centimeters over on this side. Over on this side, the weight only moves up maybe 2 or 3 centimeters. Oh, that's interesting. I wonder how that could be. Well, let's investigate the ideas of conservation of energy. Yay! Okay. Let's take a look back here about conservation of energy. So, get that out of the way. And then we're going to draw this thing again. So, yeah, okay, good. Like that and like this. So we had this heavy weight on this side, and then we had the walrus or person or whoever it is pushing down on this side. When we push down on this side, we're applying a force onto this side of the lever. We're applying a force over here. And then over on this side of the lever, that's going to transfer into a force on that side of the lever. We've got two forces to keep track of here, so we're going to call this force in. On the input side, we're pushing down on this lever, and then this is going to be the force out over here. Now, of course, we like to shorten things, so we'll just write this as F in, and we'll write this as F out. And what we notice is that for this one, in order to lift it up, this was 200 grams, so that required 2 newtons of force to lift it up. So I know that my output force was 2 newtons on this side. It takes 2 newtons of force to lift it up. My input force over here was less than 2 newtons, which seems strange. It seems like you're getting something for nothing. You're pushing down here with a force of maybe 1 newton or half a newton, and on this side, you're getting an output force of 2 newtons. Well, luckily, Walrus and Tiger were very clever, and they realized that another part of the equation actually has to do with distance. And if we look over here, the distance that Walrus and Tiger pushed down was way bigger than the distance that the actual weight moved up. So we have 2 distances over here, so we're going to call this distance in and this distance out. Let's see what happens when we apply conservation of energy. So we have the work that happens on the input side has to equal, I'll do it over here, the work that happens on the output side. So the work on the input side has to equal the work on the output side. The work on the output side is force times distance. So we have force out times distance out equals force in times distance in. Sometimes people call this the Findin-Fout-Dout equation, which is pretty fun. And what we can see is that I only have to have the multiplication, the product of force out and distance out times force in, distance in. They have to be equal to each other. So for example, if my force out is 2 newtons, if I have a smaller distance out, let's say 1 centimeter, then my force in could be something like 1 Newton, and my distance in could be 2 centimeters, so that they all equal out. And this is the idea of what we call a simple machine. A simple machine is something that allows me to have a smaller input force and a larger output force, and consequently that means I need to have a larger input distance and a smaller output distance. When I multiply them together, then they're still going to equal each other. Now technically, we should really be doing things in terms of meters. So let's erase this, and let's call this 0.01 meters and 0.02 meters. And then we can see that the energy on the input side and the energy on the output side of the work are going to be the same. So 2 times 0.01, that's 0.02 joules. Newtons times meters equals 0.02 joules on this side. So energy-wise, we cannot get anything out of a simple machine. A simple machine is not going to add any energy to the system. We're just using the clever idea that I can adjust my input distance and output distance in order to change the amount of input force and output force that we're going to use. There's also what comes along with this is the idea that we call mechanical advantage. Mechanical advantage is going to be a measure of how much easier was it to push on this side than to push on this side. Energy-wise, it's all a wash. The joules input is going to equal the joules output. But if I have a smaller force here and a bigger force here, then we can get what we call a mechanical advantage out of that. So mechanical advantage is going to be how much easier it was to do it. Was it 5 times easier? Was it 10 times easier? And that's a pretty easy formula. It's just going to be your output force divided by your input force. So in this particular situation over here, my output force was 2 newtons, my input force was 1 newton, so my mechanical advantage is actually just going to be 2. That means it was twice as easy to lift it up. I got an output force of 2 newtons, and my input force was only 1 newton. You can also list mechanical advantage. Mechanical advantage can be in terms of input and output distance. So this is going to be distance in divided by distance out, like that. And over here it was 2 centimeters divided by 1 centimeter, so we still get 2 for the mechanical advantage. Either way you want to do it, it's either going to be output distance over input distance, or output force over input force, or input distance over output distance, and that's how you're going to get mechanical advantage. And there's other types of examples to do this. There's pulleys, there's ramps, screws, lots of ways you can get mechanical advantage and to build a simple machine. Okay, thanks.